Hi, welcome to my presentation today. The topic is deep learning based mammography image segmentation. This project was completed at Oil. Here is the calendar for today. I will first introduce briefly about the topic and its background, then describe the provided materials and the experiments during the thesis. Then the result will be presented with short discussions and finally the conclusion. Firstly, mammography images is a type of medical image which are acquired using X-ray technology. The task is to segment an image into different regions of interest. For example, regions can be background tissues and medical objects. To do so, the current method that is being used is a thresholding base combining with manual refinement. However, there are two main problems with the current method. First, despite the similar images in the same image type, the acquisition condition varies. This leads to great differences in output images, meaning with the same threshold values, it might not work for the new images. To adapt with the new image, effort must be made. The manual refinement step is often required to improve the segmentation accuracy for newly acquired image. It is suggested that applying deep learning approach could solve these major problems of current method. Therefore, the output of this is a prototype software. This software will implement a deep learning model to perform segmentation tasks on mammography images. The developed software should provide comprehensive options to study the dataset, pre-process the images, to perform model building, and then evaluate the result. To accomplish the goal, tests will be conducted in an experimentally manner. After each of these experiments, the segmentation performance will be evaluated by performing quantitative and qualitative analysis. In addition, there will be comparison of segmentation performance between the deep learning and the current approach. Next is the background. Let's take a look at the background for the main step to accomplish this thesis. First, preprocessing is a step to prepare the input data for the deep learning network in further steps. This would include these tasks: labeling, one-hot encoding, and augmenting images. Labeling is an essential and important step to, let's say, tell the machine about the region and its corresponding class. Labeling also helps to use the labeled images as the ground truth images to compare with the predicted mask later. There are several well-known tools to label the images. For example, snap or even ImageJ. However, snap is used in this thesis because of it was developed specifically to label the medical images. On the other hand, ImageJ is more like a general image analysis tool, despite it offers a wide range of features. Then, one-hot encoding is a step to encode a class to the numerical form, and the image augmentation is to generate new images with, let's say, slightly varied data from the original ones, but it should still keep the meaning of the image. There are approaches offering multiple augmentation methods. For example, as you can see here, augmentation, image output, or built-in function of the keras. Then the augmentation method could be a file transformation, horizontal or vertical flips, zoom, shift, or etc. Next one would be the networks, the deep learning networks. There are three typical types of state-of-the-art network architecture in recent years that have been studied for medical image segmentation field. They are full convolutional network (FCN for short), UNet architecture, or generative adversarial networks (GAN). And then they are, let's say, common metrics to use in segmentation task as well. They could be accuracy, IOU, or dice coefficient. Dice coefficient can be called dice score later on in this presentation. The loss functions are listed here as a common one, but then they must be chosen carefully because each of the loss function might or might not able to deal with let's say specific difficulties like the imbalance of classes. Here is the slide about the experiment setup. The scope of this thesis will include 6 different datasets. The dataset will be studied for its characteristic. As you can see, the 6 datasets here, well, with different names, but they are actually different types of mammography images. Each type was taken for different purpose and used different equipments. The summary of the dataset used in this thesis is in the table below. As you can see here, the first table shows that they have different size and quantity. The quantity is obviously low in number, which is also a difficulty to train a deep learning model. For this thesis, there will be 3 classes, which are generally the same for all image types. These classes are background, thesis, and any other objects, in which, well, this other object will be different depending on the image type. Furthermore, a pixel will belongs to one and only one class, following by the one-hot encoding steps, which will encode the classes of background, thesis, and object into 3 classes, denoted as class 0, 1, and 2 respectively. Then the table also shows the corresponding encoded array. You will later see the result of this encoded mask. The graph 2 are the mask that was labeled using the indication that I already mentioned earlier. These graph 2 images will be used for training, predicting, and evaluating later. Okay, now let's say the base network that was chosen is the UNet architecture, and the developed software will provide multiple options for 3 phases, as I mentioned: training, predicting, and then evaluating. To reduce the complexity of the problem, the following training parameters are fixed. For example, the learning rate will be 0.001. The size of the input images, or also known as data point, would be 256 by 256. This would decrease the computational resources needed for processing while training the training set. The bytesize will be 8 here. Well, actually, it will be hardware limitation, so the bytesize can be only 8 maximum. The training and the testing set ratio should be 90-10. Image augmentation are performed on the fly and then modified depending on and modified later depending on the empirical data. Experiment data are recorded for further investigation or reproduction for further purpose like using in the production environment. Okay. Now, from the setup that has been already presented, the experiments will be conducted with the following focuses. Firstly, there will be experiment to select the suitable matrix to evaluate the segmentation performance. And then the first type of experiment is to create a simple pre-processing pipeline for the input images. Secondly, it is to find out the correlation between the loss and the diet score. This is to see if it is possible to evaluate the performance based on only loss or diet, or should we use a combination of both. After choosing the appropriate matrix, the experiment focused on optimizing segmentation performance will be conducted. There are mainly 3 categories using different image augmentation methods, training with different number of training data points, and then identifying the problematic images. Now, it's time to have a look at the result. First, the result from pre-processing step. I will break down this step into several sub-steps. The first one should be labeling, or also called fine-tuning mask. It is the step in prior to any other steps. As you can see, this is a typical research where masks were generated by the current method, which provide many incorrect reasons. The upper part of the left part of the images. Therefore, the ground truth must be fine-tuned to have the better standard. As you can see on the right side, these 2 masks are reliable using ITK snap based on the original images. After the fine-tuning mask step is done, augmentation methods are selected and being done on the fly in training phase and when starting the software. Slide here is an example that I saved the augmented images for debugging purpose only. This debugging step is also important because it ensures the augmented images are meaningful and could be recognizable even by the human's eye. Otherwise, the model will learn irrelevant information and could cause greater errors on the output. Next is to ensure the one-hot encoding is correct as well. As mentioned earlier, the mask will be encoded with 3D arrays, 3-dimensional arrays. The selected encoded masks are also for debugging purposes only. These colors RGB, red, green, and blue, corresponding to each of the encoded arrays. For example, as you can see on the slide, the blue was the array of 001, and it should be the background. The red one will be 100, which will be the class 1. That should be the thesis here in the medical context. And the green is 010 will be class 2. That means the any other medical objects, that not the other two. Finally, after all above steps are ensured to be correct, a simple pre-processing pipeline is built. This slide shows an example of input images, also known as data points, after the pre-processing is done. Saving images out is for debugging purpose only. And again, it is to ensure the input images are correct before the training phase. Okay, let's have a look at the matrix selection step. As mentioned earlier, there are multiple potential metrics can be used. The common ones would be accuracy. However, it might not be an appropriate metric to be used in the segmentation task. This experiment is to select the correct metric for this task. As you can see, the accuracy score on this chart right here is always, let's say, quite high, around almost 90%. But then the corresponding mask are not satisfy the requirement. The class 2 are totally incorrectly predicted. Why so? The reason is when in an image, if there are, let's say, 5% of the class 2 and 95% of non-class 2, then when the accuracy says 95% is correct, this might mean it correctly guessed the non-class 2 pixels only. Therefore, a better metric for the image segmentation task should be used. From here, this shows the intersection over union and the dice score to evaluate the performance. Generally speaking, both metrics take into account the overlapping region of the class 2 and the predicted mask, and it should provide a better number to evaluate the performance. As you can see from the chart, both IOU and DICE has significantly lower value compared to the accuracy, and it reflects in the predicted mask as well. The next experiment is to determine the correlation between loss and DICE scores. The desired result is the negative correlation between them, meaning when the loss decreases, the DICE score should increase. As you can see from the chart, which reflects the result of 6 datasets here, the results are as we expected. However, there were some trials that the DICE score does not increase that much compared to other trials, even it does have negative correlation. This runs reaches the point where the DICE score becomes stable too early and the performance cannot increase anymore. Of course, there will be experiments trying to improve the segmentation from this point later. Now it's the time to answer the two research questions, which are the segmentation performance of the deep learning approach on 6 datasets and how the segmentation performance differ between the deep learning approach and the current method. The upcoming slides will show the segmentation performance of 6 datasets and also quick comparison with the current method. Both quantitative and qualitative analysis should be presented. First, on the Mammo 2D, most of the masks generated from current method were good enough to use undergrad tools, so in this case, the current method could be considered as the golden standard. The slide shows the best run where deep learning approach has a score around 95%. When compared to the graph tools, there was a small number of pixels are not correctly predicted. However, this can be fixed by post-processing, but this is not in scope of this thesis. Therefore, the deep learning approach at this point can help with reducing the human effort on manual refinement for this dataset. On the second dataset, the deep learning approach has like 97% for the data score, and based on the medical purpose and the predicted mask, especially when you consider the third test image here, like the image 2 here. The deep learning approach has significantly better segmentation performance, and this should be a preferred approach over the current method. In this mammal specimen mark is for multiplication, which is I consider it as the most difficult dataset where both the deep learning and the current method perform poorly. As you can see, the deep learning approach only has around 85% of the score for the best run, while inferring from the predicted mask, deep learning approach gives a bit better result, but this is not yet satisfies the medical requirement. Next one would be the mammal stereo biopsy. The score result by the deep learning approach was around 91%, but then when we compare with the current method, the problematic last test image here was significantly better using the deep learning approach. For all the test images, post-processing can be done to fix the minor incorrect regions. So I would say the deep learning approach might be preferred over the current one. For this mammal modification, as you can see, the dice in the deep learning approach was at 3%, but the predicted mask was generally better in comparison with the mask generated by the current method. As you can see, especially for the last image, the background and thesis in the deep learning approach was significantly better. It did not predict the incorrect regions like the current method on the upper left corner. The last dataset is the mammal small mark. Despite the score was only 84%, but it was not yet the best trial. The reason that this status stopped here because the deep learning approach already provide the results that satisfy the medical requirement. So deep learning should be preferred over the current one in this dataset. The next three experiments are to optimize the segmentation performance to have a better assessment and whether the image augmentation correlates with the other segmentation performance. It is necessary to carry out the experiment with different augmentation methods and their corresponding parameters. You can see here the example result chart show the fluctuation in the performance when using the augmentation methods. And as can be seen, there are methods that give significantly better performance than the others at the same approach. From this, we can determine the method that's suitable for each dataset. Next one is the experiment about the experiment of different number of data points. It is meant to see if this number of data point might correlate with the segmentation performance. Well, it is already known that the number of data point is directly correlated with the number of epochs. So these experiments are conducted at different number of epochs. As the chart shows, there are improvements in segmentation performance, but it was not as significant when it already reaches this zero point. The last experiment was to find out the problematic image in the test set. Then this problematic image can be restudied for the statistic. And based on that, the performance can be improved. This experiment is meant to be this time when evaluating and then starting a new training image without actually looking at the predicted mask. Okay, comes to the conclusion. To conclude, this thesis already developing a prototype software. This software apply the network to perform the segmentation task on the mammography images. The evaluation was performed on datasets using both quantitative and qualitative analysis. In quantitative analysis, there was strong correlation between loss and dice score. Therefore, the dice score can be used as the metric for this purpose. The obtained lowest dice score was 84% for the mammoth spotlight, and the highest one was 97 for the mammoth specimen. In qualitative analysis, the results were assessed based on medical purpose, and some of the results might be preferred over the current method, and some might not. This should depending on the medical purpose. And after evaluating the predicted mask. So the first research question was answered by combining the quantitative and qualitative analysis, and the second research question was answered by the comparison between the results from the deep learning approach and the current method. I think that's it for today. Lastly, the future work. While the aim is to improve the segmentation performance for the problematic cases, especially in the dataset mammoth specimen and stereo biopsy. Implement post-processing pipeline for the predicted mask to smooth out the edge between the partitions. And lastly, it would be beneficial to fully automate all the steps from pre-processing, training, evaluating, and maybe post-processing data. Okay, thank you. This is end of the show.